Well, greetings, peeps. Back at it. This time, our topic is projectile motion. Number one about projectile motion, very key to it working the way it does on Earth, ignoring air resistance, of course, is the fact that there is no horizontal gravity. Ain't happening. So what that means is that AX, the horizontal acceleration, is 0 meters per second squared, which also means that our starting horizontal velocity is equal to our horizontal velocity for the entire phase of motion. For as long as the object is moving through the air, the initial horizontal velocity, which is v naught x, equals the current horizontal velocity, vx. Very important piece here. What we want to try to do first to set up the problem is evaluate v naught. That looks like v6. It's not. Taking theta, the angle theta, to be the angle with respect to the horizontal, we have this over here. So we've got in the horizontal, in green being horizontal, green is grass, right? So v naught x is the same thing as v naught times cosine of theta, okay? Because what we have here is v naught projected at some angle theta that we said is going to be taken with respect to the horizontal. So this angle here, we notice the adjacent side relative to this angle, so it's related to the cosine of the angle relative to the hypotenuse. If we look at SOHCAHTOA, the cosine is related to the adjacent hypotenuse. So here we go. V naught x is equal to v naught, which is the hypotenuse, times cosine of theta. V naught y is related to the sine of theta. So v naught y is equal to the v naught times sine of theta, and that's the vertical part of the initial velocity, original velocity, v naught. These are called components. These are vector components. So they've been broken down into perpendicular pieces because that's the way we need to evaluate the motion in two pieces that combine together to form one set of movement. And that's the horizontal piece and the vertical piece. The vertical, as you noted, is blue. So with blue, we've got pointing towards the sky or from the sky. So vertical is blue, horizontal, green. There are three scenarios. Let's take a look at those three situations right now. Scenario number one. The angle of launch is 90 degrees. That's our situation. Okay? What does that mean? Well, it means that the object is fired straight up and falls straight down. Like so, up and down. And I've established a neat, dandy coordinate system here that indicates that the positive direction is up. That's the blue vector. Green vector to the right. That is positive for the horizontal. And my g is down relative to this. So this suggests here when our launch angle is 90 degrees, you can see it's the right angle here, and here's theta. V naught is just going to be projected entirely. All of that velocity is going to be upwards, totally vertical, and it goes up, reaches its peak, and then comes back down. We've done problems like this. We've done situations where we studied, for example, the air rocket launching, going straight up, and also with the human jump. So, like so, we wanted to get our hang time here, and this would be a situation where theta is 90 degrees. This is actually a one-dimensional problem, so I kind of tricked you here, but it is a situation that's covered by this when the angle is 90 degrees. Now, what we're going to do is have the angle all horizontal. That's scenario number two. But it's not a one-dimensional problem. This is fully two-dimensional. So scenario two, the angle of launch is 0 degrees. This is what we know as half a bool of motion. Half a bool of motion, because it makes a little half a bool in the pattern like that. So the object is launched horizontally. V naught is totally horizontal. So V naught is really equal to v naught x in the x direction, okay, because it's all moving this way. V naught y is 0 meters per second because this thing is starting at the peak, and you'll notice that it's traveling completely horizontally here. There is no initial vertical velocity, therefore v naught y is 0. Okay, so let's look at what happens here. I've established again my coordinate system. It's very, very important. We want to indicate which direction is positive, which direction is negative. Positive going up, blue vector, and that indicates vertical. Green vector going to the right, that's positive, gravity going down. So we have an object. It has this horizontal velocity. It's being thrown off of this pier, and it moves in this hyperbola. So here are some of the other key attributes. We have dy. dy is the height here from the ground to wherever the object launched. dx is the horizontal displacement, how far it traveled with respect to the edge of the cliff or the pier here. And here's what happens when it lands. We have a combined velocity v that's made up of the components v naught x in the horizontal. Why is it v naught x? Well, we'll get to that again. Well, I'll remind you. And v naught y. No, sorry, just vy. Just vy. Not the v naught y is 0. Vy is completely different. We have a vertical velocity because of the acceleration due to gravity over this height. And then we establish this black vector over here, which is the combination of the two, the vector combination of the two from the components, perpendicular components. And this is theta, the angle. All right, this is v naught x because there is no horizontal gravity. Ax is equal to 0 meters per second. So throughout this entire flight, we're going to have the same velocity horizontally. So if we started off at 5 meters per second, we end at 5 meters per second in the horizontal motion, but we've gained some velocity, of course, in the fall. And that's what happens when we combine it over here. So to get v, we would need some trigonometry. So good thing we studied that about a month ago. We would go with Pythagorean theorem, perhaps, or SOHCAHTOA to get this angle, and there you go. What are some examples? Well, we might study some cliff-style problems. So an item that's launched off a cliff. How far does it land away from the cliff, for example, if we know the height of the cliff? Flugtag! Flugtag is amazing. You will love it. It's from Red Bull. It's hilarious. And basically, there's this pier in costumes and sort of a skit, and these weird contraption machines that are supposed to fly, but almost always they never do. So Flugtag. I just noticed that this looks like Cuff. I think I made that comic book mistake. Wait a minute. Good thing I don't have that comic book font. This is Cliff, not Cuff problems. Cliff problems, just so you know. All right, now you were reading it going, that doesn't say Cliff. Yes, it does. And also an airdrop package. So I'm going to go through the situation, the one that's covered in the book, between pages 65 and 67. Is that what it is? 65 and 67? Yep. So an airplane with a package drops it. It's moving at some horizontal velocity, and then the package lands, and so we want to know how far away from that initial point the package lands. And so that's another type of problem that's carried by scenario 2, angle of launch is 0 hyperbola, otherwise known as type 1 projectile motion. Which then brings us to scenario 3. The angle of launch is somewhere between 0 and 90 degrees, okay? Theta is greater than 0, less than 90, so it's in between. We're launching it at, an angle relative to the horizontal as well. So here's the situation. This is the fobola. Fobola motion. Object is launched vertically and horizontally at the same time. Yes, just like north and east is northeast. We have verhor, no vertical, horizontal. Okay, so how does that happen? Again, my coordinate system. Plus goes in the up direction, and that is the vector for going to the right horizontally. G, hey, we've seen this before, but it's very, very, very important to specify it every time. There'll be a time when we actually rotate our coordinate systems accordingly to fit the problem. So it's important to get in the habit of drawing it along with the entire scenario here. So suppose we have an object, it's given a v naught that has an angle relative to the horizontal. It's some part v naught x and v naught y to begin with. So it's going to have some original velocity of both. As it moves through the air, it's going to make the fibula. Here we go. It reaches a peak in the middle of the flight if it's symmetrical, if we launch and land from ground, for example. Over here, the Vy peak is 0 meters per second because it's going to start coming down. It's no longer ascending. It's going to start the descent. So that means the velocity in the upward direction will decrease due to gravity until it hits 0 and it comes back down. But we still have the horizontal piece that's moving forward here to the right. So v naught x is still going to be the same as it was over here. In fact, it's the same all the way up till the very moment it's going to land. So the distance here from the ground to the maximum height is called dy peak. It's an important piece as well. We might want to know, how high did this object go? Is it able to clear, if we fire an object, is it going to clear a certain hurdle, a wall, a castle, I don't know, something of the sort, the school, you know, like maybe our air rocket? No, I won't do that. But maybe we want to know if it's going to, like in football, if there's a field goal, something of that sort. The horizontal piece, the dx, is this full thing here. It's called the range. What is the range? It's what is the maximum horizontal displacement that this object will move in the horizontal direction when you fire it. And there are ways to tweak the angles and optimize that too, something we can also play with the air rocket. And also, this is very similar to what it was in the half-fibula. We have v here as the combined vector of vy and v naught x, okay, in the horizontal and in the vertical. And this guy over here is going to be the vector combination of these two components. So we build it just the way we would before, Pythagorean theorem, or if you know the angle, then you can use SOHCAHTOA. Okay, so one more thing to introduce in this introduction to projectile motion beyond these scenarios are the 2D motion variables. So let's bring that over. So what we have here is a graphical grid. I will give you a copy of this that's not on chalk, actually on paper, that you can use, where I've divided up into three categories here because the variables, it's very important to note that the variables do not cross. In other words, if you work with your equations of motion on the vertical side, you never use components from the horizontal side, and vice versa. You would never use vertical pieces here on the horizontal side. But there are some attributes that are shared, particularly time, because vertical and horizontal will always be matched when they share time together. It's kind of romantic. There's a little tale about Horace and Vera. It says Horace don't know what Vera's doing and don't care. In other words, they have independent motions. They don't really care if one is moving at 20 meters per second, the other one is accelerating up and down. But this is the very sweet part. But the time they share tracks where they are as a pair. It's brilliant. They do. So they share time, and we could find out where they are as a pair, and that's where the object is in the half-fibula of the fibula. Okay, let me just describe these variables, and then later on we'll do a problem in another video. Horizontal, dx, that's how far it's gone horizontally from its initial spot. V naught x is v naught times cosine of the angle. We saw that before. Ax is always 0 because there's no horizontal gravity and we're ignoring air resistance effects. Now, because Ax is 0, this means here that Vx, the NEx velocity, is the same thing as the initial x velocity, which is v naught x. Okay, these are going to be the same throughout its entire flight. There's nothing that's going to speed it up while it's in the air or slow it down, unless you have, again, wind or something else, but there is no gravity to do that. Ain't no horizontal gravity. We'll talk about what happens. I'll show you in the end if there were some horizontal gravity, what it would look like. Ugh. So here we got our coordinate system that I placed over here because I had some space for it. On the vertical side, dy, that's just the height of the object relative to the launch point at any moment. V naught y equals v naught times the sine of the angle. Okay, this is the initial starting vertical velocity. Vy peak is where it's we filled it in this value of 0 meters per second because the Vy will be slowing down as it ascends until it gets to that point where it descends. And then Vy will be the velocity at any moment, maybe at the end if we want to look at it. And Ay is equal to g, which is the acceleration due to gravity. And relative to this coordinate system here, it's negative 9.8 meters per second squared. Shared values. They share the angle at the very beginning. The angle changes as it moves, though, which is an interesting thing to note. V naught, they share, and we break it up into the components, horizontal, V naught cosine theta, V naught sine theta. And V is the velocity at any given moment, particularly maybe at the end we're interested in it. And then we've got T peak, how much time did it take to reach the peak of the fibula, and what's T total. So those are the things. Now, as promised, what if there's horizontal gravity? All right, what kind of mess would that make? So if I had horizontal gravity, then we might have it go in a certain direction. It'd be a problem because we would just kind of be pinned to the ground like this into the corner, and it'd be like jumping off of the wall forwards, and you'd fall back to the wall like that. And that's what would be kind of a mess. So, we still have vertical gravity. So that would be a very bad thing. There ain't no such thing as horizontal gravity. So there's your introduction to projectile motion. Upcoming next is the half-fibula type problem. I'll run through the case that's in the book where the plane drops the package, and we'll still use our 11-step method to solve the problem all the way through. And that's our start with two-dimensional motion. Whew. Thank you. All right. Morad. Oak.